Hello everyone, welcome to the class. And in today's class we are going to see few concepts, right? We have already covered what is an electric potential and capacitance. So in today's class we'll just recap some of this and we will try to solve some numericals. Along with this, we will also try to learn what is the relationship between your electric field and your electric potential. Alright, that's an important equation, which let's see that equation as well. Okay, so once again, my name is Mohana. I'm a physics educator here at Unacademy. So if you're taking your class 11 and 12 physics, I'll be teaching. And this is my Telegram channel link. So in case any update before the class goes live or anything, right, would be shared here. So you can follow me on my Telegram channel. And here, this is the common Unacademy ICSE and ISC both channels. So you can follow this channel as well. All right. Now, just like how we have these free classes on the Unacademy on the YouTube channel, right? Unacademy YouTube channel. Likewise, we also have free classes on the Unacademy platform. Those we call it as special classes. All right. So you can learn from any of your favorite educators, right? And you can special classes are absolutely free. Okay, and you can engage with these educators via pool feature. Right now, since these special classes are also live classes, you can get your doubts solved then and there. All right. Now, the link for the description, the links for the upcoming special classes on the Unacademy platform, right, is in the description box. So you can just go to class 12, click on the link, and it will take you to the upcoming special classes. All right. So here, if you see, tomorrow, that is actually 30th June, we have a topic. So in the beginning of the month, I said, like, on the YouTube platform, we were actually covering your Unit 1 and Unit 2, right? On the Unacademy platform, right, there we were actually covering your Unit 2 and Unit 3, right? So here, this class is the last of this month, okay, pull to magnetism. So we'll be continuing from wherever we have left in the last class. So basically we learned what is Biot-Savart law, and we also saw some applications of Biot-Savart's law, right? So whatever is left out of that, we would continue seeing that, and we will also see how is Biot-Savart law different from Ampere-circuited law, okay, or if they are same. All right, that we will cover in tomorrow's class. Once again, the registration link will be below. You can click on the class 12 link. It will take you to the upcoming classes. Just click on this class, notify, and before the class could go live, you would be notified for the same. Okay. Now, tomorrow's class, it's also a session. In case if you have any doubts in any of the classes we have done in magnetism unit, any doubts you have till whatever concepts we have done till now, you can ask me for the same as well. And we will also do a few numericals. Now, the next class after 30th June is on 2nd July. All right. And this class, again, we would be covering a topic, your Unit 2 topic, that is DC circuits and measurements. All right. This is going to be on 7:45 p.m. on 2nd July. Okay. Then after that, on 7th July, at around 7:45 to 8:45, so at about the same time that you're taking these YouTube classes, okay, we have another topic, that is moving coil galvanometer. Right, this is again from your Unit 3. Right, so these are the upcoming special classes. There are actually more special classes than this, but the next 3 upcoming special classes are shared here. All right, and if you're interested in the Plus subscription, so these are the advantages. One is you can learn from the comfort of your home. Next is, whenever you're taking a Plus subscription with Unacademy, you're getting 4 subjects. That is physics, chemistry, math, and biology. Okay. Now, all these 4 courses, if you're getting right, you will get unlimited access to all of these 4 subjects. Okay. And all the educators on the platform are really good. So you'll be learning from the top educators, and they would be every 4th session. Okay. Every 4th session is always a doubt clearing session. All right. So if the class starts today, 4th class from today will always be a doubt clearing session. So there are always regular doubt clearing sessions. So if in case you missed, okay, any of the previous sessions, and if you watch the class recordings, okay, then you can actually, if you have any doubts, then you can ask during your doubt sessions. All right. And your Plus subscription, we will be covering your entire syllabus, and there are always more practice tests available, right? And also every other week we have live test series. Okay, in the live test series, right after the test series is over, there will be an analysis session where you can, there will be a step-by-step solution to how to solve the questions you would have attempted. Okay, now there are some upcoming batches and courses, so you can check out that as well. Now before going to that, I have the if you see the Unacademy Plus subscription, the longer duration you take the course, right, the price the price per month goes down. Okay, and you will actually use my my educator code MTIS10 to avail a 10% discount on the same. Okay, and also we have an exciting information for you guys now. That is, you will get between 22nd to 30th June if you're taking the Plus subscription. Okay, then you're getting 20% off on the ISC board Plus subscription. For example, as I said, the longer duration you take the course, price per month actually goes down, right? See, if you take 9 months course, the course is 11,960 rupees. But if you're taking for 1 year, that is just 13,800, right? Now that is the current price you will be paying. Okay, so you will be saving around, if you're taking the 1 year subscription, you will be saving around 3,450 rupees. And if in case you're in class 11, for 2 years you're just paying 23,000. You're saving 5,750 rupees. So this offer is only between 27 to 30th June. Okay, so between these days, if you're taking, that is before tomorrow, in case if you're interested in the Plus subscription, but tomorrow if you're taking the subscription, you will get a 20% off. All right. To get the subscription, you can again, to avail this particular discount price, you can use my code MTIS10. And then if you're taking 1 year subscription, you can just get the course for 13,800 rupees. Okay. Now, with this note, we also have an upcoming class 12 batch, or actually this is an ongoing batch. The target of this Achievers batch has been your midterm syllabus coverage. So we are targeting to cover your first 5 units, and also this the course delivery, okay, the course will be taught in English. Okay, for physics we meet every Monday, Wednesday, Friday between 5:15 to 6:15 p.m. Now the target, why we started this course earlier, is that moving forward in the year, right, you'll have more revision time. That was actually the original plan. Right, so here if you see this particular course, which started on June 1st, in case if you have missed any previous classes, you can always watch the class recordings, and there will also be upcoming classes, right, normally revising all of those units as well. Okay, so then with this note, let's begin the class today. Okay, we are starting with a very simple concept. Okay, because first we'll once again see the basics of what is electric potential. Alright, I'm going to give a quick basics about all of these concepts before moving on, right? But if you have any doubts, you can actually ask me. Now, if you say that, let's say there is a charge, and if the charge is actually a positive charge, right, then the electric field line will be radially outward. Okay, now this electric field line over here, right, what is the equation connecting it? It is very simple. Let's say if you introduce a test charge Q0. So test charge will always be a positive charge. Now this test charge will, because this is a positive charge, this is also a positive charge, this test charge will experience a repulsive force in this direction. Right? This will be the repulsive force in this direction. Now the electric field line is pointed radially outward. Now this force experienced per unit charge is actually electric field. So your electric field is nothing but force per charge. So you can say the SI unit will be Newton, right, per coulomb. That's your SI unit of electric field. So electric field is always force per charge. So one more way of saying what is force. So electrostatic force is also equal to electric field, right? Electric field times charge. Alright? Alright. So you can actually say, if you have any questions, you can ask me in the chat box. Alright? Okay. So you can, from here you can actually say, we just saw electric field was nothing but force per charge. Right? So electrostatic force will be field into charge. Okay? Now, this is your basic definition for electric field. Right? Now, for a positive field lines, for a positive charge, the electric field is radially outwards, and if you see, the charge is spherically symmetric, meaning it's just like, it's like, everywhere around, if you see, right, the electric field lines are equally distributed, right? And it's the same. So in this case, if you can say that the electric field lines in case of a positive charge are always pointed radially outwards, and that of a negative charge, they are always pointed radially inwards. Okay, so a positive charge electric field line diverges. For a negative charge, the electric field line converges because they are pointed radially inwards. So the electric field line starts at the charge and ends at infinity. Okay, now what is a potential difference? So what is the difference between electric field and potential difference? As we have seen in one of the previous classes, right, that there are two ways to define the electric field lines around the charge. One is by the electric field equation that we saw right now. Another is using your electric potential. Okay, for example, let's say there is a positive charge. Okay, so if this is a positive charge, then the electric field lines will be pointed radially outwards. So your direction of the field lines are in this direction, right? This is your electric field line. Now let's say I introduce a test charge over here. Okay, test charge Q0. What will happen? Right? Here it will experience a force this way. Right? Now against this electrostatic force, if you're moving this charge, right? If you're moving this charge from this point, okay, to, let's say this is point A, right, to point B. Against the electrostatic field, you're moving this particular charge. That is, you're moving this charge from point A to point B. And you're doing that against the electrostatic force. Okay, so the work done in moving the unit positive charge, right, or the positive charge, okay, in from one point to another against the electrostatic force is basically called as your potential difference. Okay, now that potential difference, so at this place this will have a potential difference VA, and let's say this is a potential difference VB. Okay, why? Very simple. Okay, at this point, because as the field lines, right, the field lines as the distance as in the distance increases, the intensity of the field line drops. So here, more than at this point VB, we may require more force to push it. So as you're moving from point A to point B here, you might need more force to push, more force you have to, the work done will be even more against this electrostatic force. Because here the electrostatic force of repulsion will be low, but here when compared to this point, here it will be less. So you're increasing as you're trying, work is done in moving the charge from this point to this point, the repulsive force is also increasing, so work done is also more, right? So now this potential V, right, in potential difference V, in moving from VB to VA, that is from point, the potential over here to potentially over here, this gives you the total potential difference, right? So this potential difference is nothing but, okay, work done in moving the charge from A to B, okay, right, this gives you the potential difference. So potential difference between 2 points in an electric field, you can define it as the amount of work done in moving a positive charge from one point to another against the electrostatic force. Okay, now, right, so what would be the unit of electrostatic force? Right, over here the unit is work done, right? In this case the unit is basically given as the SI unit is basically given as 1 volt. Okay, and this 1 volt, okay, potential difference unit is 1 volt. This 1 volt is nothing but work done. What is, if 1 joule of work has to be done in moving a unit positive charge, wherein the charge also have 1 coulomb magnitude, okay, from one point to another against the electrostatic force, that gives you the definition of 1 volt. Okay, so here we can say 1 volt is equal to 1 joule coulomb inverse 1. Okay, now this is potential difference. Now what is this electrostatic or electric potential? That is again a very simple concept here. Again, let's say there is a positive charge. Okay, since it's a positive charge, the field lines are pointed radially outwards. This time what we are going to do is, instead of, we are going to bring a unit test charge that is somewhere at infinity, meaning there is no influence because of this positive charge, there is no influence at this position of this charge over here. So here potential will be basically, potential at this point over here will basically, let's say this point is VA, let's say this point is A. Potential at this point is actually 0. Why? Because this is not in this, see, there will be field lines everywhere, but still this charge is actually not, this positive charge is still not in the influence of this field, okay, of the source charge. Now if you slowly start moving it, okay, now there might be some field line somewhere in this region. As you slowly start moving it into the field, right, into the electrostatic field over here. Let's say this point is VB. So this point has a particular potential, okay, that is VB, right? So if you move your charge somewhere from infinity, okay, to the the work done in moving a unit positive charge from infinity to the point on this point on this electric field, right, in the influence of this electric field. So when you're bringing this point against the electrostatic force of this particular charge, right? So if you're bringing the point unit charge from infinity to here, then we call that as electrostatic potential, and that electrostatic potential will be what? It will be VB minus VA, right? VA is 0, so this will be just VB, which is equal to work done in moving a charge from infinity to this point, right, by the charge. Okay, again, so from here you can simply say that electric field, okay, electrostatic potential, when you're talking about electrostatic potential, is nothing but right, potential is nothing but work done by per charge. Again, this will be 1 volt, the unit is 1 volt, work done over here is nothing but 1 joules, and charge is nothing but has a unit of 1 coulomb. So 1 volt is nothing but work done in moving a 1 unit of coulomb of charges from infinity to a point against the electrostatic force. Okay, that will become the definition for electrostatic force, that gives the definition for your electric potential. Okay, again, potential and potential difference and potential, this is the difference between them. Now, what would be the electrostatic potential due to a point charge? Let's say that you have a point charge, okay, let's say there is a charge and this is again a positive charge, right? Let's say this is positive charge. Now, because of this charge, let's say at some point, okay, from from some point in infinity, okay, from some point in infinity, you're bringing a charge, okay, to a point P inside this field. Till here, see, let's see, there is the field influence is only till up to this point. Okay, because of this positive charge, the field influence is only up to this point. I mean, it starts and it ends at infinity, but still, but somewhere from infinity, you're bringing a charge. Okay, so if you bring a positive charge, let's say first it was in point A. From here, you're trying to move it into point B. Okay, so you introduce a positive charge over here, that is Q. Now the force of repulsion, electrostatic force of repulsion, will be in this direction. This will be the direction of the force. Okay, but you are trying to displace it, right? Let's say this is O. From here to the point P over here, let's say the distance is actually R. Okay, from here to the point A over here, let's say the distance is actually X. Okay, now what will be, according to this Coulomb's law, right, F, the electrostatic force of repulsion between the source charge and the test charge will be 1 by 4 pi epsilon naught Q naught divided by X square. Alright, so this is the charge over here. Now, this is the distance between them, right? X is the distance between them. Now, if you move this charge by a small point, let's say from A to B, if you're moving them, then the displacement, it's happening, right? The total distance from Q to A is X. From A to B, when you're moving, that small displacement will be given as dx. Now, what is the work done, in the total work done in moving this charge from A to this point Q would be W, means what is the work done in moving this particular charge from A to B? That will be dW. Will be what? Work done will be electrostatics. The work done will be for the how much force is applied for this particular unit charge to move from one point to another. That point is nothing but dx. Right? Both are vector quantity. Right? Now, if you want to find the magnitude, f dot dx dot product means it will be cos theta. Okay? Now, the distance, this distance dx is in this direction, right? The distance dx is in this direction. Now force is in this direction. So angle between them is 180 degrees. So if you want to find the magnitude of the same, not in vector, but if you just want the magnitude, so this will be f dx, right? Cos theta. Theta over here is nothing but 180 degree. Okay, cos 180 degrees. Hello, good evening. Cos 180 degree is actually minus 1. So you'll have minus f dx will be the answer, because cos 180 degree is minus 1. Okay, now this is the work done in moving the charge from just point A to B. From here, if you want to find out what is the total work done in moving the charge from infinity to this point B, right? From infinity, you're moving this charge to point B. What will be the total work done? Okay, that will be integration of this quantity. Okay, so that will basically be integrating dw, okay, and integrating f dx. But within what limit? You're bringing this charge from infinity, right, to this point P, right? Somewhere from infinity, you're bringing it to point P. At point P, the distance is r. So you're integrating it between infinity to r, right? So here, what is the equation for f over here? Right? So let's just do this alone separately. Okay, just a second. I'm really sorry, just give me one moment. Okay. Alright, okay. Really sorry about that. Just a second. Right, okay. Now, right, now this integration dw, okay, will actually give you work done. Okay, so you're integrating this, right? There's a minus sign, right? From infinity to r, okay, f dx. So integration of infinity to r, okay. What is the value of force over here? It will be 1 by 4 pi epsilon naught q naught divided by x square into dx, okay, into dx. So you can take all the constant quantity outside. 1 by 4 pi epsilon naught you can take outside, q naught also you can take outside. All you will have is, you will have 1 by x square into dx. Okay, 1 by x square. This quantity is nothing but 1 by x square is nothing but x to the power of minus 2. Okay, now integration of x to the power of minus 2 dx is very simple. Right, this is nothing but, okay, this is nothing but minus, okay, this will be minus x to the power of minus 2 plus 1, right, by minus 2 plus 1. Okay, there's, sorry, not minus, I have taken this commonly here. Okay, so minus 2 plus 1, in this case it will be minus 1, and minus 2 plus 1, again in this case it will be negative, minus 1. Okay, so this quantity is nothing but, you can just take the minus sign outside, right, over here, and then you'll have 1 by x. X to the power of minus 1 is 1 by x within the limit infinity to r. Now this minus sign you can take it outside, so you'll have q naught divided by 4 pi epsilon naught. Okay, you bring the limit inside, this will be 1 by r minus 1 by infinity. 1 by infinity is again 0, so if you see work done, or W is equal to Q naught divided by 4 pi epsilon naught, okay, 1 by R. Okay, this is the value of W. Right, this is work done. So we have actually found out what is work done. So work done was 1 by right, 1 by 4 pi epsilon naught q naught by R. Now electric potential is work done per charge. So you're going to divide this entire equation by q naught. Okay, so you're going to divide this entire equation that you have over here by q naught. Okay, so if you divide by q naught and q naught will get cancelled. So finally you will have this electric potential is nothing but electric potential, right, due to a point charge. Okay, so now that we know this, right, let's try and solve a very simple question. Okay, let's say work done. So let's say you are moving a charge from point A to B. Okay, right, and the work done in moving the charge from point B to A, right, from this point to this point. What is the work done? Okay, that work done is given by, we want to find out what is the work done. Okay, the charge that is being moved over here, the charge value is around 3 coulombs. Okay, 3 coulombs of charge is being moved from, let's say, point A to point B. Okay, for 3 coulombs of charges being moved from a point A to point B. Point A to point B, let's say this is around point B to point B, and 3 coulombs of charge, right? The charge over here is 3 coulombs. Okay, now, right, so from here you're moving the charge here. So let's say there is a positive charge or negative, some charges over here, and this is actually the direction of that particular force. Okay, now the potential at the point A is 2 volts. Okay, and the work done, right, the work done is actually given as well. Let's say the work done is again 18 coulombs, 18 joules. W is actually 18 joules. Right, now if you're moving the charge from here to here, okay, what is the potential at B? Is the question asked. So once again, I'm checking the questions from your books, from your reference books. All right, now here potential difference is given as work done by a charge. Potential difference, this V is nothing but, okay, what is the potential at B minus what is the potential at A? Potential from moving, this is a positive charge and this is a positive charge as well, right? So the charge Q is again positive. So if you're moving this charge against this electrostatic force of repulsion, in this point it is around, the potential is minus 2 volts. Now as you're going here, the electrostatic potential at point B will be different. That's what we want to find. But to move from here to here, work done is actually around 18 joules. Okay, now here if you say VB, we don't know, we have to find, but we know the potential at the point A is minus 2 volts. Okay, work done is 18 joules and charge is around 3 coulombs. Okay, so here if you use that, now this will be VB will be equal to 18 by 3 is actually 6, and this charge minus into minus, it becomes plus, right? So this will be 6 minus 2. And the potential at B at this point over here is going to be 4 volts. Okay, all right. Now, now let's say we actually want to find out. Let's do one more numerical from based on the same. Right. Now let's say there is a charge here. Let's say there is a source charge over here. Okay, let's say the charge over here is around 4 into 10 to the power of minus 7 coulombs. So it's a positive charge, right? Positive charge will be going radially outwards. Now somewhere from infinity, you're moving a charge, you're moving a test charge to some point P over here. Okay, now now this charge over here, right? Okay, this distance P, from this charge to this distance P, okay, this distance is around 9 centimeters. Or actually you can take, around 9 centimeters. Okay, so somewhere from infinity, you're moving a test charge to this point P. Okay, test charge Q0 to this point P. And that point P from the source charge is 9 kilometers away. Let's say the source charge is at point O. Sorry, 9 centimeters away, not kilometers, I'm sorry, 9 centimeters away. Okay, now, so which means this value gives you R. So if R is equal to 9 centimeters, means centimeters in terms of meter will be 0.09 meters. Right? Now, first thing we want to do is, okay, we want to first calculate what is the electrostatic potential. First, what we want to find is what is the potential at this point P. Okay, potential V at this particular point. Potential is given by what? This equation we just saw, 1 by 4 pi epsilon naught Q divided by R. 1 by 4 pi epsilon naught is a constant quantity which is 9 into 10 to the power of 9. Right? This value, okay, into what is the charge? Okay, charge over here is nothing but 4 into 10 to the power of minus 7 by what is the distance? Distance is 0.09 meters. Right? Or you can write as 9 into 10 to the power of 2 meters as well. Right? So you can write this as 9 into 10 to the power of minus 2 meters. Right? This value as 9 into 10 to the power of minus 2 meters. Now, so potential will be this 2 cancel. So you will have is 4. Okay. Into 10 to the power of 9 into 10 to the power of minus 7 into 10 to the power of minus 2. When it comes up, it becomes plus 2. So 9 minus 7 will become 10 to the power of 2. 10 to the power of 2 into 10 to the power of 10 square into 10 square. Right? That becomes 4 into this quantity becomes 10 to the power of 4 volts. Okay. That's the potential at this point P. Okay. Now, we know the potential at this point P is this value. Now, what will be the work done in bringing this charge from infinity to here? Okay, work done is actually given as, okay, we know potential is actually given as work done per charge. So work done will be potential into charge, potential into unit charge, right? So this test charge over here, right? Right. So in this case, if you see, the test charge that you're bringing from infinity to here, that Q0, the test charge has a value of, let's say the test charge has a value of 2 into 10 to the power of minus 9 coulombs. That, so previous case what we saw, because of this charge at this point, what was the potential? Because of this positive charge, source charge, what was the potential? Now, against the electrostatic force, right? If you're bringing a test charge which has a value of 2 into 10 to the power of minus 9 coulombs, right, from somewhere from infinity to this point P, then what is the work done? What is the work done from bringing the charge from infinity to this point P over here? Okay, now that is given by potential into this Q0. What will be the potential value over here? Potential we just found at this point, the potential is 4 into 10 to the power of 4 into Q. What is the source charge value? That is 2 into 10 to the power of minus 9 coulombs, right? So the work done will be, this would be around 8 into 10 to the power of 4 minus 9 will be minus 5 joules. Okay. So to bring a unit test charge from infinity to here, it takes around 8 into 10 to the power of minus 5 joules. So if you're bringing a Q0, that is test charge, which has a charge of 2 into 10 to the power of minus 9 coulombs from infinity to this point. So the work done is given by this. Now at this point, what is the potential because of this charge is given by this equation. Okay, so I hope this is clear. If you have any further doubts, again, you can ask me in the chat box. All right. Now, after this charge, after this, right, we also saw, we also saw that what was the potential due to a point charge, right? We also saw that the potential due to a point charge is spherically symmetric, as it depends only on the distance of the observation point from the charge and not in the direction of the point with respect to the point charge, right? That is, the potential is infinity at 0. As we saw in the earlier case, I said the potential at infinity is 0, and it just depends on the how much distance it is from this point charge, right? Now, as I said, positive charge has charges the electric field lines for a positive charge are pointed radially outwards. For a negative charge, it is pointed radially inwards. Now, what happens in case of a dipole? Okay, that is, if you take two charges separated by a small distance, in this case, both the charges have the same magnitude. So, if this is plus 2 coulombs, this is going to be minus 2 coulombs. Okay, then the electric field lines, okay, tend to start at the positive and terminate in the negative. Right, it is no longer radial, or it's no longer straight, it is bending, right? In this case, right, now between two positive charges, right, between two charges, if you take two charges, that is, if it is a dipole, meaning if this is minus 5 microcoulomb, this has to be plus 5 microcoulomb. The distance between them, let's say the distance is actually, the distance, mostly the books takes it something like this, right? It takes from the center to the center point O over here. This distance will be taken as A, okay, and this distance till here will be taken as A. So, the total distance from between these two would be taken as 2A, alright. Sometimes it will be taken as 2L also. Instead of A, some textbooks use L as well. So, the dipole moment, it is a vector quantity and the direction is always from negative to positive charge. This dipole moment is actually just tells you what is the strength of an electric dipole. Is nothing but what is the magnitude of any one of the charges. Why? Because if both charges have the same magnitude, it's just that one is positive and another is negative. Magnitude of one of the charges into the distance between them. It's a vector quantity because charge is a scalar, but here position vector, if you're taking for A, right, that is a vector again, right? This gives you the equation for dipole moment. It just says dipole moment over here is nothing but unit will be coulomb into, right, coulomb into coulomb per meter, right, coulomb meter, that is its unit, alright. So, here what will be the electric potential, right, at a point on the dipole, right? So, on the axial line. Now, because of this electric field lines, right, at this axial point, if you're saying, let's say I want to take at some point over here, let's say I'm taking a point P over here, what will be the potential because of this electric dipole? We've done this in one of the previous classes, so I'm just going to give the equation. Okay, this potential is going to be 1 by 4 pi epsilon naught, okay, P divided by R square. Okay, R square being the distance taken from the center of the dipole to this point P. Okay, this distance gives you R. Okay, in case of an axial dipole, in this case, V is proportional to 1 by R square. Okay, now in case of an equatorial, now let's say how much of a distance, let's say you are moving, for example, let's say you are actually only going, let's say this is 5 meters, okay. Now, the same dipole from the center, you have to go 5 meters, okay. Now, at this point, what will be the potential? Okay, that we actually saw, this point, the potential will actually be 0. The potential of, because of both these things, both these dipoles at this point will be 0. Okay, so if you're looking at this dipole, okay, on the axial line from the center, let's say I'm going whatever distance, this R that I'm going, at this point, if I calculate what is the potential is actually, in this case, will be 1 by 4 pi epsilon naught Q by R square. Okay, but same distance from the center, if I go a distance R and if I see what is the potential at this point, this will be 0. Okay, so what we will do is, we will calculate what is the electrical potential, but at some random point, right? We will see what happens in case we are taking the electric potential, but in this case in a random point, right? For example, let's say there are two charges, right? So let's say this charge is minus Q and this charge is plus Q, and the distance between these two dipoles is actually 2A. Okay, now we're going to choose some random point over here, not equally, but some random point P. Okay, now from the center of this dipole, which is actually over here, right, to this point P, this distance is actually given by your R vector. Okay, now from this end to here, this distance will be R1. Okay, and from this point to here, this distance will be R2, because this is a little bit more than this. Right? Now, okay, here you can actually see, okay, from here you can actually say the potential. So we can give all of these quantities a name, right? You can say this is actually A, B, right? So AP is actually R1 and B to P is actually R2. Okay, so the net potential at this point P will be the net potential at this point P. Okay, what is the total potential at point P? That will always be the sum of the potential because of the charge Q minus Q, that will, let's take that as V1, and the charge plus Q, let's take that as because of V2. That is, at this point, if you from infinity, if you want to bring a charge to this point, that will be against the electrostatic force, or since it being a test charge. So over here, if you're bringing a test charge, since it's positive, it will be against the electrostatic force of this charge and against the electrostatic force of repulsion of this charge and electrostatic force of attraction of this charge. Alright, so in this case, so let's see what is V over here will be 1 by 4 pi epsilon naught. Charge over here is minus Q divided by R1 plus 1 by 4 pi epsilon naught. Okay, this will be Q divided by R2. Okay, so here, okay, we will take most of the quantities, like, Q is actually common, right? We can take that 1 by 4 pi epsilon naught can be taken outside. So all you will have is 1 minus 1 by R1 plus 1 by R2. So I'll write that as 1 by R2 minus 1 by R1. Okay, so here again we can write this as, okay, this could be R1 minus R2 divided by R1 R2. Right, this is R1 R2, right? Okay, now what is R1 minus R2? Which distance gives us R1 minus R2? We need to see. Okay, let's consider this as a triangle, right? This case, let's say from here, let's make this a triangle. So from this point, if I draw this, this becomes an equilateral. Let's draw this triangle over here, right? In this angle over here becomes a right angle. Okay, this angle is theta. If this is theta, this is again theta, right? If this distance is R2 and this distance is R1, from here, see from here, this distance is R2 and this distance is R1, just this distance will be R1 minus R2, will be this distance. Whatever is R1 minus R2 will give you this distance. Okay, that is this value over here. Then what is, let's try, okay, now let's say if the point P is very far away, okay, then this R1 and R2 distance really doesn't matter. Okay, then we can say this R1 and R2 are almost same. Okay, so instead of using R1, okay, if the point is very far away, okay, this point is very far away, then this distance over here, the difference between this distance will be very small. For example, this could be okay, this point could be somewhere around let's say this distance is 2.1 meters and this could be 2.2 meters, right? That's a very small difference, right? Okay, so in such a case, okay, then such a case we can say R1 is equal to R2. So R1, R2, which is equal to R, we will equate that to R. So R1 and R2 we can take it as R square, saying that we both are equal. Okay, now what, so R1 and R2 we have solved this one. So what about R1 minus R2? This quantity over here, since this is theta and this could be a right angle triangle, so let's take this angle as theta, right? This is a right angle triangle. So if I want R1 and R2, okay, so this one you're going to get it if you take cos theta, right? Cos theta will give you this side by this side, right? So if you take cos theta, that will be R1 minus R2, this side over here by this side, which is actually, this length is AB, right? This length is AB. So R1 minus R2 is nothing but AB cos theta is nothing but R1 minus R2. But AB is just the length of the dipole. So AB is nothing but 2A cos theta. So we can actually substitute all of these quantities in this equation. So you will actually get Q divided by 4 pi epsilon naught. R1 minus R2 is nothing but 2A cos theta divided by R1 and R2, you can take R square. Now, this quantity that you're seeing over here, right, Q times 2A, this is actually equal to the potential. Okay, this is actually equal to the potential. So here you can actually say, right, so here you can actually say this potential over here, okay, alright, Q into 2A is nothing but dipole moment, okay, and so you can say 1 by 4 pi epsilon naught, right, dipole moment P cos theta divided by R square. What we're going to do is, we're going to multiply and divide by R, okay, so let me do that separately. So if you multiply this quantity, that is 1 by 4 pi epsilon naught, okay, then we have P cos theta by R, right? You're going to multiply and divide by R, right? When that happens, you will actually have V is equal to 1 by 4 pi epsilon naught, okay, this is being R square, right? In this case, you will have P dot R cos theta. Cos theta is a dot product. So you will basically have P R cos theta. Cos theta is a dot product, right? In this case, it will be R cube. Since it is a dot product, okay, now this equation actually becomes 1 by 4 pi epsilon naught, okay, P vector dot R vector, okay, P vector dot R vector by R cube. I'm sorry, in this case it will be by, this is actually R, right, this is actually R square, okay, so it becomes R cube, okay. Now, this R vector, if you want to, this R vector, you can write it in terms of unit vectors, okay. R vector is nothing but the magnitude, okay, the modulus of R vector into R cap. So R vector is nothing but modulus of a vector gives you the length of the vector. So R into R cap, okay. From here, you can actually substitute this value over here. So V will be 1 by 4 pi epsilon naught, okay, P vector dot, instead of R vector, you can write R into R cap divided by R square, R cube, okay. Then you will have 1 by 4 pi epsilon naught, okay, R and R square you can cancel, so you will have P dot, so here you will have actually P dot R unit vector, right, unit vector R by R and R square cube cancels over here, no, you will have R square, okay. Now the unit vector, okay, with this unit vector R acts along this, will act along this vector, this line joining here, okay. So finally, the equation that you're getting is actually V is equal to 1 by 4 pi epsilon naught, magnitude equation will be P cos theta divided by R square. That's the magnitude of this potential equation, right? In case if you want to write it in terms of vector equation, then it will be 1 by 4 pi epsilon naught, right? P vector dot R vector divided by R cube, right? That's the vector equation. So this is the this is for the point that lies at any general position. Okay, now okay, so between the points, if it is lying between this axial, if the point is lying between the axial, okay, if the point is lying in this end, okay, if the point is lying on this end, if you want to move a charge somewhere on this end or this end, okay, there's two special cases that we need to see. One is if you want to bring a charge point towards this end, or let's say you want to bring in or if you want to move bring a charge, okay, to on the axial line somewhere on this end. Okay, in both cases, right? So this case will be theta is equal to 0 degree or 180 degree, right? In this case, your potential will be, we saw that 1 by 4 pi epsilon naught, right? PR cos theta by P cos theta by R square, right? Now this cos theta being by R square. So if the cos theta is actually 0 degrees, cos 0 is basically 1, right? Then you will get V is equal to 1 by 4 pi epsilon naught P by R square, okay? But if this is 180, cos 180 is minus 1. So this quantity becomes minus. So along this axial line, if the point is at 0 degrees or 180 degrees, okay, that actually that whether it's 0 or 180 depends on this position vector. Okay, now in this direction, if you see, okay, if you take a point here, the dipole moment is in this direction, right? And your R vector is also in this direction. In this case, theta is equal to 0 degrees. But if you take a point P on this side, right, from this center to this point, this will be R, right? Now this R is in this direction, right? The R in this case, from the center to the point P that you have chosen, the R is actually in this direction. Dipole moment, this direction, this is P. Now if you see, the angle between them is 180 degrees. Okay, so theta equal to 180 degrees. So if theta equal to 0 degrees, that is the dipole moment is in alignment with the position vector R over here, then we get a positive value. But if it is if these two directions are different, then we get a negative potential, that V is equal to minus 1 by 4 pi epsilon naught P by R square. Okay, so you get the greatest possible potential when theta is equal to 0 and theta is equal to 180, you get the greatest negative potential. Now, if the potential is lying on the equatorial line, okay, in this case, the angle is what? In this case, the angle is 90 degrees, right? When the potential is in the equatorial line, then the potential is actually 0. For theta equals to 90 degrees, it is actually 0. Potential is 0. Theta equal to 0 degrees, V will be equal to 1 by 4 pi epsilon naught, that is somewhere on this point over here, P. Okay, this will be 1 by 4 pi epsilon naught Q by R. Right? Sorry, P by R square, this is not just Q. In case of, if you're taking in terms of dipole moment, then this will be P by R square. Somewhere over here, if you're taking potential in this point, will be when theta is equal to 180 degrees, then it will be V is equal to minus 1 by 4 pi epsilon naught P divided by R square. Okay. Okay, here if you see, at this point, potential is 0, but electric field at this point is actually not 0. Electric potential in this place is negative and this place is positive, but everywhere around the field exists, and everywhere around, whether it's been on the axial field or the equatorial field, electric field doesn't go 0. It's not 0. Okay, only the potential at this point is 0. Electric field at this point is not 0. Okay, alright. And from that note, before we end the class, okay, a quick note is that let's just see what is the what is that equation connecting electric field, okay, and electric charge, right? So if you have a point charge, as I said, okay, and let's say this charge is a positive charge, it has let's say it's point so over here you can see that this is the direction of the electric field lines are radially outwards. Now if I bring in a positive charge over here, if I bring in another positive test charge over here, the force of repulsion will be in this direction. This will be your electric field force. So electric field at this point is given by what? Okay, electric field at this point is given by force per charge, right? So here you can actually see, okay, this force you can say is nothing but, this force, right, is nothing but Q0 into E. But if you see over here, when we are talking in terms of electric potential, we are talking about moving this charge from a point to another point against this electrostatic force of this charge, right? So because of that, the force over here, see, the force is in this direction, means because against that force you're trying to move, the electric field is in another different direction. So there is a negative sign. Okay. Now if you want to bring the charge from point A to point B against the electrostatic force, so with terms of force, it will be F is equal to minus Q into E. So if you want to move it from this point to this point against the electrostatic force, okay, then that work done, we saw many times, right? That work done is given by force. What is the force in this case? We are moving against the force into the displacement. This small short distance displacement is dr. Okay, and the force over here is minus Q0 E dr. Okay, we saw that work done is nothing but, we also know potential difference is nothing but work done per charge, right? Potential difference is nothing but work done per charge. From here you can actually say work done is nothing but potential difference into charge, right? So here, okay, potential difference again is given by, okay, potential difference in this case, again, in this case, this potential difference is given by what is the potential at this point A, that is VA, minus what is the potential over here. So potential difference is actually given by VB minus VA, right, into the charge. The charge in this case is Q0, because you're moving this charge against this, right? So you have work done, one equation, right? So we have another equation for work done also. So let's equate both of them. That is minus QE dr, that is how much you're displacing from this point to another, right? So from this point another, and this will be equal to this value over here, that is Q0 into VA minus VB. For the small displacement, the potential will be dV. This difference between these two potential will be dV. Okay, will be Q0 into this potential VB minus VA, no, this potential difference, right? Moving the charge from point A to point B, that potential, that's just very small. We are not moving it all the way. A very small distance you're moving on this, on the electric field line of this source charge. That is actually dV. That potential difference is dV, right? From here, Q0 on both sides gets cancelled, right? So you will have minus E dr is equal to dV. So from here you can actually say E is equal to minus dV by dr. This quantity is called as your potential gradient. Okay, now, all right, now from here if you see, your dV is nothing but minus E into dr. If you integrate them, if you integrate on both sides, you will get, this is the potential, this is the equation connecting your potential to the electric field. If you integrate on both sides, you will get the potential is nothing but minus electric field into the displacement, that is R. Okay, or you can say dr in this case. Right, so that gives you this particular quantity, and this will be let's say whatever the distance between these two that you're moving, right? So this V would be basically minus whatever distance you're moving between, right? Integrate that within those two limits into E into dr. Okay, but here the equation that connects is potential is nothing but electric field into the displacement, how much it is getting displaced, right? That is the dr over here. Okay, it's an important formula as well to remember. Okay, with this note, we are coming towards the end of the session. Once again, before I end the session, right now the course price is 20% off, right? So if you're taking a plus course between 27th to 30th June, right, you're getting a 20% off. So if you're taking a 1-year subscription of 13,800 rupees, you're saving up to, you're paying only 13,800 and you're saving up to 3,450 rupees, right? So basically, you can use my code MTIS10 to avail this 20% offer, and this offer is only between the time period of 27th to 30th. So it ends tomorrow. So if you're planning to take a plus subscription, now would be the great time to take, okay? And you can use my subscription code to avail the offers. In case if you want a 9-month subscription, then you will be paying you will be saving 2,990 rupees and you'll be paying 11,960 rupees. For 1 year, the course price you'll be paying is 13,800 rupees and you'll be saving 3,450 rupees you'll save. Alright, so once again, if you have any questions, you can ask me in the chat box. And there is an ongoing batch. This is an achiever batch. The target is for this course is going to be a mid-term syllabus coverage. So the mode of delivery is going to be in English. The course starts on 1st June and it's sort of and in case if you have any classes that you have missed, class recordings will be given. We started this course quite early so that moving forward in the year, you will have more time for revision. And for physics, we meet every Monday, Wednesday, Friday between 5:15 to 6:15 p.m. Once again, whenever you're taking a plus subscription with Unacademy, you're taking the subscription for 4 subjects. You're getting math, physics, chemistry and biology. So for 1 year, if you're paying this price, or for 9 months, if you're paying this price, okay, for both cases, you will be getting all 4 classes. Okay, and a minimum of 10 classes for each of the subjects as well. Okay, so in a month, there will be a minimum of 20 classes. Sorry, 40 classes in total, minimum classes, right? For class 11 also, we started another batch. The target of this batch is your midterm syllabus coverage. So term 1 syllabus will be covered. Once again, you have, in case if you're taking class 11 subscriptions, if you're taking your class 11 subscription, you're in an advantage. Class 12 subscription is absolutely free for you guys. And you're getting 4 subjects. And if you're taking only for class 11, class 12 is absolutely free. And with the 20% offer, you're just paying for one year, but you're getting the benefits for 2 years. Once again, to avail the offer, you can use my code MTIS10 and the offer gets over by tomorrow. Okay, so if you're planning to take a plus subscription, take it now. It will be the best time to take it. And once again, we are introducing a community feature. So there's a link in the description box. You can go to so you can use that link to go towards my community. So using this community, if you are actually following me on the community, you will not miss any updates. And also, if you go to my community, there will be some MCQ type question asked. Okay, try solving them. And Bugs Bounty is another thing where you actually, if in case you find any inappropriate content in any of the videos, and if you report the same, you can claim your prize. Okay, and if you like the class, please share it among your friends, and also subscribe to the channel so you are always so you can know about the upcoming classes, and click on the bell icon to get notified as well. All right, thank you guys.